Okay, so I'm gonna go ahead and do 2.2 or 11.2. 11.2 is all about the second derivative. So if you remember with the first derivative, we went through and we were looking for where our graph increases, where the slope increases, and then where it decreases. Where it goes up and then goes down, that's our maximum. Where it goes down and then up, that's our minimum. Okay, so first derivative is all about increasing, decreasing slope. Second derivative is all about concavity. So remember when we were talking about, my dog's right here. When we were talking about second derivative, we were talking about how things curve. So as an example of that, if I had a function that curved, let me get a better pen, that curved down like that, that means we have a downward concavity. So you could think of it as a cup that's turned over, like a teacup that's turned over. The concavity is curved down. So what happens is it slows down the progress, or it speeds up the progress. If we have a function that curved up like that, now we have a concavity that's positive. So when it curves down like this, that's a negative second derivative. When it curves up, that's a positive second derivative. So again, concavity and second derivative go together. What we're going to look for is what's called the points of inflection. So points of inflection, you can think of it as when we were in the first derivative, we were looking for critical points. In the second derivative, we're looking for possible points of inflection. So what that means is where things change. So when this goes from concave down to concave up, there's a point right in that area where it went from going down to going up. So we can call this point right here the points or the point of inflection. Okay, we're going to abbreviate it to POI. Okay, so our POI is connected with our second derivative. So what's going to happen is, remember when we were doing the first derivative, I kept trying to emphasize the fact that make sure you label everything. If you're looking for the first derivative, you're looking for the increase and decrease. If we're looking for second derivative, we're looking for the concavity and the points of inflection. So you have to keep those two separate, because what's going to happen is we're going to put everything together. We're going to be able to graph a very accurate graph based on first and second derivative. Okay, so with second derivative, you really do go through the same process as when we were finding critical points and where things are increasing or decreasing. It's the exact same process, except for now we're working in second derivative instead of first derivative. Okay. So I got to find my paper here. That's not it. Okay, so second derivative, remember, is just finding the derivative of the derivative. That's all it is. I'm looking for, hang on, I'll be back. I have so many papers everywhere. This is crazy. Here we go. Okay, now I got it. Okay, so second derivative is all about concavity, points of inflection. Okay, so same process. So when we're looking for second derivative, let me write out my function. So if you notice, this is the same function I used when I was teaching the first derivative and finding where it increases and decreases. We're going to go through the same process. We're going to get our first derivative, and then we're going to get our second derivative. So first things first, you're going to find the second derivative. So can't do that going directly, so we have to go through the first derivative first. So again, using power rule, drop this to the front and then subtract 1, drop this to the front and subtract 1, drop this to the front and subtract 1. So that should look very familiar. That's what we did on Monday. So this is my first derivative. Now I'm going to find my second derivative. Okay, so same thing. 2 times 3 is 6. Subtracting 1, 1 times 6 is 6, and subtracting 1. Now I have my second derivative. So, excuse me, so just like, excuse me, just like what we did with our first derivative. Now we're going to set that to 0. Okay. I can't cough and teach at the same time. So set the second derivative to 0. All right, just like what we did with the first derivative. So I go 6x plus 6 equals 0. And then we're going to solve for x. All right, so this is fairly simple. Divide both sides by 6, and I get x equals -1. Now, what you just found is the possible points of inflection. Now, remember, it's possible. It may not be the actual point of inflection or where it goes from down to up or up to down, but it's a possible one. So this is the same thing, same idea as our critical points. These are the values that we're going to use on our test chart. So the next step, once you found your possible points of inflection, now you're going to set up your test chart. Okay, so I'm going to have to erase this. I'm going to rewrite that. So we have our second derivative was 6x plus 6. Our possible points of inflection was x equals -1. So now I'm going to set up my test chart. Again, label your test chart so you know exactly what it looks like. All right, you know, okay, this is second derivative. So second derivative, the only possible point of inflection was -1. So I'm going to put that on my number line. Now I have, this is broken my number line up into 2 intervals. So if you notice, we're doing the same thing as we did with first derivative. So that's why it's so important to know which one are you doing. Are you doing first derivative or second derivative? So set up our test chart, and let's identify where the concavity. So we're looking for concavity. So here's the difference between the first derivative and the second derivative. Remember, with first derivative, we were looking for, is our slope increasing or is it decreasing? Is it going up or going down? Now what we're looking for is our second derivative curving up, which means we have a positive second derivative, or is it curving down, which means we have a negative second derivative, okay? So with this one, we know that our possible point of inflection is actually a point of inflection when we have a difference, when we go from positive to negative or negative to positive. So anytime there's a change in the interval, then we know that that's actually a point of inflection. How do we test it? Well, we do exactly what we did before. We pick a value in this interval. So this interval is between -infinity and up to -1. It doesn't include -1, but it's up to -1. So I don't want to use -1. I got -1 by setting this second derivative to 0. So if I plug -1 back into my function, I'm going to end up with 0 again. Okay, so don't use the actual possible point of inflection. Use a number within the interval. So I'm just going to use an easy one. I always go to 10s, 1s, 5s, you know, something that's easy to use. So if I plug -10 in here, I get 6 times -10 plus 6. Again, I don't care about the actual number. All I care about is my answer positive or negative? So I get -60 plus 6, which gives me a negative value. So this section, this interval, has a downward curvature. In other words, it's concave down. Okay? Notice with second derivative, I'm using curves. I'm not using arrows anymore, because arrows indicate that the slope is increasing or decreasing. With second derivative, I'm indicating that the curvature is increasing or decreasing. Okay? Now I jump over here to my other function, or my other interval. I'm going to use +10. I could use 0. 0 works. So let me just use 0. 0 is an easier number. Remember efficiency. Okay, so 0 is bigger. It's in this interval, so I can use 0. So again, I don't care about the actual value. All I care about is my answer positive or negative? Well, I end up with a positive value. So I end up with positive on this side. Positive means my curvature goes up. The concavity is up. So what this tells me, since I have a negative and it switches to a positive curvature, what this tells me is this -1 is actually a point of inflection. That means when x is -1, that's where my graph is going to change curvature. It's going to go from down to up. Okay? So the last step then is once I found my test chart and once I found my concavity, if I find an actual point of inflection, now I need to find out, okay, what value of y, so how high up or down on my graph is that point of inflection actually happening? So I have to take this -1 and I'm going to plug it back into the original. We did the exact same thing with the first derivative. We used first derivative for the test chart. Once we found our max or min, we plugged the answer back into my original function. Same thing with second derivative. Second derivative, we found the actual point of inflection. Now we're going to use that point of inflection and plug it back into the original function. So I'm going to get -1 cubed plus 3 times -1 squared minus 9 times -1 minus 11. And when I work that all out, I get -1. -1 squared is 1 times 3 is 3. -9 times -1 is plus 9, and then minus 11. So I get 2 plus 9 is 11 minus 11. So my point of inflection is at the point -1, 0. What that means is I have a point on my graph that my graph goes from curving down to curving up. Okay? So if I were to graph this very quickly, I know that at -1, 0, so at that point right there, something is happening on this side, and I know my curvature is down because my test chart tells me. At this point right here, it switches and starts curving up. Okay? Now, with the first derivative and the second derivative all pushed together, we can graph very accurately. We're even going to be able to find our where it changes, where our maximum is, where our minimum is, and then now we can find the point of inflection or where the curvatures change. Okay?